Hi, my name is Paritosh Kelkar and I am a graduate student at the University of Pennsylvania. In this lecture, we are going to cover the concept of rigid body transformations, understand why it is important in our system, and learn how ROS handles this for us. I'll give you one very good reason to continue watching this lecture. You will be able to do that at the end of this week's lectures. We are getting closer and closer to real autonomy. In the previous weeks, we raced around the corridors by essentially flying blind. We just followed the wall. We need to make our system smarter, less environment dependent, more autonomous. Mapping, localization and planning are very crucial elements of autonomous driving, and we are going to understand these concepts step by step. We start off with the basics, rigid body transformations and implementation details in the robot operating system. This lecture is divided into two parts. In part 1, we will cover the importance of the frames and transforms. What are frames exactly, and what is the meaning of transformations between them? We will go over the theoretical formulation of these concepts as well. In part 2, we talk about ROS and how it handles these concepts. From this lecture on, we start going into specifics about the software stack that is running in the car. We go into a couple of important points regarding ROS, and there will be a bunch of related hands-on tutorials accompanying these lectures. This is a very simple video that clearly showcases the concept of different frames of references or points of views. It's just basically different ways of looking at the same point or world. We'll now see how we have different frames on our car as well, and why that is important to us. Alright. Let's dive into the lecture. During the lecture, I might refer to terminology that you haven't come across before. I wanted to introduce you to a couple of terms that will be used very often. You will see this term being used quite often when people talk about frames and transformations. This frame is the most intuitive and easy to understand. The sensor's frame of reference essentially means we look at the world through the eyes of the sensor. The sensor may be a camera or a depth sensor. That's all it sees and that's all it will tell you. The sensor doesn't really know or care about the map frame. It doesn't associate objects it sees with respect to the map. It tells you how far away an object is with respect to the sensor alone. We are responsible for making these connections between what the sensor sees and its corresponding location on the map. Now let's take our car as the example and proceed to lay out the frames and the transformations involved. In the car that we have, we attach the sensor or LiDAR frame onto the LiDAR. This gives us the distance of objects from the LiDAR. This of course does not return the accurate distance from the center or front of the car itself. Therefore, we also attach a frame to the body of the car. We will make all measurements that are with respect to the car from this frame. The LiDAR gives us measurements or readings that have some delta x or delta z offset from the front or middle of the car. It doesn't know or care about the car frame. The front of the car will be 0, 0, 0 with respect to the car frame and some delta x 0, delta z with respect to the laser frame. The position of the frame is totally up to your discretion, and placing it in front of the car is just as an example. Throughout this lecture, we will be using ROS color conventions to represent all the different axes. Red is X, green is Y, and dark blue is Z. Note that the axes of the frames of reference are perpendicular to each other. Each axis represents a dimension, and any position in space can be represented using 3 dimensions. Let's assume this is the frame setup we are dealing with. When we race, we need to know the position of the car with respect to the map frame. We will also need to convert from the frame of the laser to the frame of the map to identify location of obstacles in the map frame. Make sure you have begun to comprehend what a transformation means with respect to frames of reference. We will be using this term quite frequently from now on. So what we essentially need is a transformation between different frames. Let's look at what would happen if we look at the world the way the LiDAR looks at it. It doesn't make too much sense. For one, we are always apparently stationary. If we see what the car was actually doing at that time, the scenario is quite different. This is simply because we are now viewing things in the map frame. I want to clarify the importance of the word rigid here. Rigid simply means that we are dealing with objects that we have a fixed structure. For example, you cannot apply the concepts of rigid body transformations to Play-Doh. Our car is a rigid body. Let's formalize the problem statement at hand. Let's say we have a frame A and we have a frame B. This B is rotated by some theta with respect to the x-axis of frame A. Let it also be at a distance d from the origin of frame A. Note the significance of the super and subscripts in this notation. Distance of frame B with respect to frame A. Let there be a point P as shown with a known location in frame B. The problem statement now is to find the representation of point P in frame A. We need a method to encode the rotation and the translation of frame B with respect to frame A. Let's look at the rotation. We need to represent the orientation of axis of frame B in frame A. xb cap, yb cap and zb cap are unit vectors of the respective axes represented using the unit vectors of the axis of frame A. We use these expressions to form a rotation matrix R. This rotation matrix gives us the orientation of frame B with respect to frame A. Let's take a moment to absorb this piece of information. So we have two frames A and B and they are oriented as shown. B is rotated by theta about the z-axis of A. Now let's take a point P expressed in frame B. In the frame of B, this point is 0, 5, 0. Now, what is the orientation of the point in frame A? Let's look at this step by step. Going according to the equation, let's first represent xb with respect to the axis of frame A. xb has the cosine component of xa, sine component of ya, and no component of za. What we have effectively done is found out the first column of the rotation matrix in question. Process this information. Our rotation matrix now looks like this, where we fill the first column using this equation. Notice that the axes are unit vectors and are left out of the matrix. The rows of this matrix signify the axis of frame A. We similarly find for the remaining columns in the rotation matrix. Now that we have R, we can represent the point P in the frame of A using the given formula. Assume that theta is equal to pi by 6 as an example. The calculated value of P in the frame of A is as shown. The rotation matrix calculated in the intermediate step turns out to be again as shown. We were able to use rotation matrices to express the position in different frames, but notice how the origins were coincident? What if the origins of the two frames are not in the same location? We need to compensate for this displacement as well. Back to our original scenario. Rotation alone is not enough. We must handle the translation between the two frames. With translation, we need to add the displacement between the origins of the frames. The updated formula is as shown. So what we have eventually done is rotate the frame and then translate the frame. We can now compensate for any rotation or translation between frames. On simplifying the previous equation, we obtain the homogeneous transformation matrix H, which is represented as shown. This was the theory and importance of rigid body transformations in robotic systems. We will now look at some implementation details in regards to some conventions, ROS and our system. Now we'll be going into some implementation details, conventions and debugging tools that ROS provides. Introducing the map frame of reference. This image has been directly taken off RViz and the same color conventions as earlier apply. The picture depicts the map of our lab as gathered by the car. The position of the frame you see in the diagram signifies the origin of the map. To know where we are in the map, we refer to the position of the car with respect to the map frame. With every cell roughly a meter, the car is maybe 3 meters in the x and a negative 1.5 in the y. To confirm the pose of the car, we use ROS topic for the ROS topic echo for the relevant topic. Notice how the frame ID is map and the position is what we estimated it to be. The map frame is used as the general long-term reference for this position. The pose of the car in the map frame is heavily dependent on the localization engine, and the localization engine is the frame authority, meaning it is responsible for publishing the pose of the car with respect to the map. So now the good thing is that all of these transformations that we talked about are internally handled by ROS, and specifically by the TF engine in ROS. As you can see, it's very powerful and very useful. ROS, however, lays down some guidelines and conventions that we must be wary of. We'll take a look at how ROS arranges these frames or expects these frames to be arranged. The REP 105 is a good reference for the conventions that ROS follows. You'll have links for these resources later on in the video. ROS maintains a TF tree between every frame and is arranged as shown. The map frame is generally the first child of the world frame. We will now move on to another important frame, the odom frame. The origin of the odom frame is the location of that point at which you began traversal, the frame in which odometry is measured. What is odometry? Notice how the definition specifically emphasizes on the fact that it is an estimate and not an exact determination of the pose. A very common example on the source of odometry are wheel encoders. These count the ticks on the wheels. Using this information along with the radius of the wheel, we can estimate an amount of distance traveled by the robot. The difference in the count of ticks in both wheels can also give us the orientation of the platform. Another source of odometry could be by integrating the commanded velocities and accelerations to a certain pose. Or, as explained in the previous lectures, we could even integrate the IMU readings. There is a problem with this frame of reference. All the sources for this measurement are error prone, and as a result, the uncertainty in the estimate grows with time. This error accumulates, leading to a drift in values. Notice how there is a high confidence in the initial position as the robot began traversal, and later on, as the robot has gone over some distance, the uncertainty in position increases. These errors could be from a variety of problems. For example, if you use slightly incorrect dimensions of the wheel, the measured distance would differ and all derived quantities would have inherent error. How will you be able to calculate these quantities when there's a slippage? The car doesn't move, but the wheels tells it that it has. Estimation using only odometry is referred to as dead reckoning. So the good thing about this frame is the fact that it is continuous. Since we are recording data directly from the actuators, there will never be a break in the evolution of data. We append this frame to the ROS hierarchy as shown. We now talk about the base link and other fixed frames attached to the robot itself. There are a bunch of frames that are attached to the robot. The interesting part of all of these frames with regards to our system is the fact that the relative transformations between them will always be the same. Example, the position and orientation of the laser will never change with respect to the frame attached to the car. In our system, the base link is attached to the car, and tracking the pose of the frame is equivalent to tracking the pose of the car itself. The odometry source established the relationship between the base link and the odom frame. The map to base link is established by the localization component. We can fix the frames of all of the different sensors on our robot using a URDF file. This topic will be covered in greater detail in the accompanying tutorials. With respect to ROS, we append the base link below the odom link in the TF tree. Since the TF package is so vital, the various elements in this system, ROS provides a variety of TF debugging tools. ROS WTF is just another tool provided by ROS. ROS run TF view monitor, all of these commands are just tools and will be showcased in the accompanying tutorials. You have learned now the concept of rigid body transformations, their importance in robotic systems. The important thing is that you also know how it is handled in ROS. In the upcoming lecture, you will be learning the SLAM algorithm. Make sure you understand the concepts that were just covered. Make sure you know your way around ROS and its TF debugging tools. Don't forget to watch the hands-on tutorials. Hope you enjoyed this lecture.